Well, good afternoon, everybody. First of all, I would like to express my deep gratitude to Professor Vyacheslav Futorny for the invitation here. It's my first time in the ICTP, and for me, it's a huge honor to be here. Also, thank you, everybody, for coming. As you can see on the screen, this is your joint with Professor Agustin Moreno Cañadas, and this work is a very beautiful connection between the categorification of some integer sequences and these Brauer configuration algebras, which are framed in the context of associative algebra. Before to start, I would like to mention, to do one special mention to Ukrainian people. I would like to dedicate this talk to the people in Ukraine. All our roots, or all our mathematical roots became from Ukraine, so I would like to express all my support and my solidarity with these people there. So I hope that everything improves as soon as possible. Well, now I would like to start with the roadmap of my talk. In the first part, I would like to explain you briefly a motivation of our work. This work is framed in the context of categorification of semi-integer sequences introduced by Ringel and Farr in 2008. After that, we try to explain some preliminary part of our work. It's the context of Brauer configuration algebra. These algebras were introduced by Green and Scroll in 2017. In this part of the talk, I would like to explain you briefly what is a Brauer configuration, and after that, we try to explain you what is a Brauer configuration algebra. And also, we introduce these two important concepts for us because we try to say that Brauer configuration algebras allow us to connect many things in mathematics and also describe many things in the nature. So I will try to explain what is the meaning of the message of a Brauer configuration and also an integer specialization of this Brauer configuration. As I told you before, this work is in the context of path algebras, so I mean quiver representation theory. And the idea is try to describe by using Brauer configuration algebras the number of homological ideals. These homological ideals are idempotent ideals in some kind of algebras called Nakayama algebras, and by using this Brauer configuration, we can describe, identify, and also enumerate the number of these homological ideals in these Nakayama algebras. And at the end, we can relate this topic with the first motivation, I mean the work by Ringel and Farr. So we can use Brauer configuration algebras to enumerate these kind of ideals introduced by Auslander, Todorov, and Plachet, and at the end we can go back to the beginning and connect all these three things which are maybe unexpected connection in this topic. And at the end I would like to show you some reference of the work. Well, I told you before the main motivation of our work is this work given by Ringel and Farr. They describe a partition formula, partitioning the natural way of natural number for Fibonacci number, but to do that they use some algebraic stuff like the Tri-Kronecker quiver and its corresponding universal cover. So they try to explain algebraic properties of these kind of algebras, of quiver algebras, by using integer sequences. In all this process, they can introduce this new sequence in the online encyclopedia of integer sequences, and also they describe some very interesting arrays to compute this partition formula for Fibonacci numbers. Until now, I say many times the word categorification of a sequence. According to Ringel and Farr, categorification of a sequence, as I told you before, means consider instead of numbers in a sequence, some object in a category. For us, we try to describe quiver representation as our main category. And the relationship between these numbers, these integer numbers and the elements in this integer sequence means something in this category. For instance, the equality between this number means some isomorphism between the objects in the category of representation of quivers. Okay, this is one of the main result by Ringel and Farr. This is the so-called even index Fibonacci triangle. This is a very interesting triangle because it has some nice properties like Pascal triangle. So for instance, you can construct all this guy in a recursive way by using some natural properties, like for instance, this called the hook properties. For instance, you can obtain this guy here, this 18, like the sum of 12, 5, and 1. And also, you can use something called like the diamond properties, which means do something like 2 times 5 plus 12 minus 4, and you recover this guy here. It's important to say that all this column here is the new sequence introduced by Ringel and Farr, and all these rows of the triangle mean something in the projective components of the Tri-Kronecker algebra and its corresponding universal work. And these rows also allow us, this algebraic information allow us to construct the partition formula to the Fibonacci numbers like this. As you can see here, you have this 7, this empty space means this 0 here, and all these coefficients are given by this triangle here. And the unexpected connection is that these numbers here are exactly the number of homological ideals which I promised you at the end of the talk. So now I will to move on that our key tool in this talk that is the Brauer configuration algebras. These Brauer configuration algebra are multi-serial algebras which were introduced recently by Green and Scroll, and we try to describe all its application and its connection with many topics in mathematics. Recently, we found a relationship between Brauer configuration algebra and a snake graph. Also, some very interesting relation between these Brauer configuration algebras and exceptional pairs. We can connect some topic of the Kiev school, some metrics problem studied by Professor Alexander Sabatsky with this new novel. And today we try to describe this connection related with the homological ideals introduced by Todorov, Auslander, and Plachet. And also we have some application of these algebras in elements of the daily life. For Friday, Professor Moreno tried to describe this application here, and we have some connection of this algebra in the traffic flow. Well, as I told you before, the idea of this talk is try to say one of these beautiful application or connection of Brauer configuration algebra in mathematics. We use this object to enumerate some ideals in some suitable algebras called Nakayama Alpebras. And at the end, we connect this work with Ringel's work related with the process of give a partition formula for Fibonacci numbers. Well, we start to explain what is a Brauer configuration algebra. To introduce this new concept, we need basically 3 steps. The first step is try to describe something called Brauer configuration. After that, we try to associate a quiver with this configuration, and by using this quiver and some relation over this quiver, we can introduce the notion of Brauer configuration algebra. As I told you before, this kind of algebra were introduced by Green and Scroll in 2017, and all these algebras are multi-serial algebras. And we try to use the properties of these Brauer configuration algebras to describe many things in mathematics and also in the daily life. Well, a Brauer configuration algebra, our first step before introduce Brauer configuration algebra is a quadruple of things. This set here is a set of vertices. It's a fine set of vertices. Here we have a set of polygons, which means that you can put in a set some elements of this set of vertices, but you can allow that a vertex be in this polygon many times, like a multiset, and we have fixed 2 basic information, something called the multiplicity function of the Brauer configuration algebra and the orientation of the Brauer configuration. This orientation means that we try to give an order between this collection of polygons. And also, we have some natural things inside this Brauer configuration. For instance, how many times one vertex in these sets appears in all the configuration. And this concept is called the valency of a vertex. As I told you, we need a multiplicity function and also an orientation. We define at the beginning of the Brauer configuration these things. Okay, some basic properties of this Brauer configuration. Some are very natural because you need that, for instance, every vertex in the Brauer configuration be in at least one polygon. Also, we need that every polygon has at least two vertices. And I need to define some vertices, some special vertices inside of this algebra, which are called not truncate vertices. Okay. As I told you, we need to do one three-step before to introduce the notion of Brauer configuration algebra. Now we have the concept of configuration, with the Brauer configuration, which is a configuration with something very combinatorial. And with this information, now I need to do a quiver associated to this configuration. To do that, we draw a vertex for every polygon in the Brauer configuration, and I should draw an arrow between these vertices when I have this relation between the polygons. Keep in mind that all the polygons in this Brauer configuration has some order like this. So when we have this relation, you should draw arrow between the vertex associated to this polygon and the vertex associated to this polygon here. Okay, this new quiver that I gave when I draw the quiver induce some basic relation. Here we have three kinds of relations, which here I skip all the details of the relation of these quivers. And a Brauer configuration algebra is not more than a path algebra, a bound path algebra given by this quotient here. And here we have an example. This is our key example for today. This is a Brauer configuration algebra, which vertices are some natural numbers, and we have n-1 vertices in this Brauer configuration, and we have n-2 polygons here, and we can induce this natural order, and we define this multiplicity function, this suitable multiplicity function for this Brauer configuration. The last slide has all the information, all the combinatorial information of our Brauer configuration. Now we can draw the associated quiver, of this Brauer configuration, and now we have this quiver. As you can see here, this algebra is a wide algebra. We have many loops here, and all the colors means special cycles inside this quiver. And also we have some relation on these loops and this path here. Here we describe all the typical relation for this Brauer configuration algebra. It's maybe a technical information, but we need to complete all the concept to say that this is a Brauer configuration algebra. In a natural way, we can define something called the message associated to a Brauer configuration. The message starts with the definition of a word associated to every polygon. So keep in mind that I have vertices, polygons, and some multiplicity function, and also one orientation. When I have this polygon, we can define a word associated to this polygon, and it's just the concatenation of all the vertices inside of the polygons. Keep in mind that you put inside of this polygon everything that you want. In my case, I put inside some natural numbers. And also in the natural way, we construct the message of a Brauer configuration only with the concatenation of all the words associated to the polygon. So this means that as in our natural language, you connect all the words, and if you connect all the words, you can give a message of this Brauer configuration. Well, this is another key concept for us. This is a concept called integer specialization. So if you have a Brauer configuration, you can associate to it a special map between this element in the vertices to another natural number. And we also, in the same way, would like to define the specialized word of this polygon, which means take the specialization of every of the vertex inside of this polygon. And we also have the message of this new Brauer configuration algebra. So you can do something like you have an abstract Brauer configuration and put all the information here in the context of natural numbers. Okay, if we compute the word associated to every polygon in our key example under this specialization, so I means you should put all the vertices in this function here. We have this work, and every word here will be in bijection with the number of homological ideals of these Nakayama algebras, which I will be explained in a brief. And here we have the message of this associated to this Brauer configuration algebra. Okay, our second stop is the stop devoted to homological ideals. These homological ideals are very useful homological tools to study derived category in the context of quiver representation theory. These ideals were introduced by Auslander, Todorov, and Plachev, and these ideals are ideals which produce this kind of homological epimorphism between this quotient map, and this homological epimorphism induce a full and faithful functor between this derived category between these algebras. So as you can see, these kind of ideals are very important in the homological stuff, and here we use Brauer configuration algebra to describe these homological ideas just in a combinatorial way and also in a graphical, easy way. We now use a proposition given by Chan He and Jose Antonio de la Peña, which say that if you have an idempotent ideal, we use mainly these two items of this proposition. If you have an idempotent ideal, we can decide if this ideal is homological or not. Just put your attention in the X functor. But compute these things for general quiver is not easy, so we have an combinatorial criteria to describe when this X functor vanish. Also, the last important information that you need from the homological stuff is try to describe how produce all the idempotent ideals in an algebra, in a path algebra. So if, keep in mind that if I have an algebra, a path algebra, I need to compute all these idempotent ideals, and after that I need to check if this condition related with X functor holds or not. So I use the trace between these pair of modules in the quiver algebra, and this trace is enough to consider the trace of the projective module over the algebra to construct all the idempotent ideals associated to path algebra. And also this very important remark by Todorov and Auslander, which say that all the homological ideals always are finite. So we can establish a closed formula for this kind of ideals. It's not easy for a fixed family of algebra, but here we give a formula for Nakayama algebras. Okay, we assume this notation, which means that if you denote this ideal with these numbers here, means that you are considering the trace of these projective modules associated to this vertex over this algebra. And this new module or this ideal is an idempotent ideal, and I need just to check when this ideal is homological or not. So I need to check this X property, which is not easy to compute. The family of algebras that we study was the so-called Nakayama algebras. Here in the talk, we put our attention in these algebras here, these AN algebras with any relation here. We also have some results in this algebra, and we have some conjecture in a general, for instance, 2P algebras or this kind of path algebras associated to these quivers. And keep in mind that we fix this family of algebras. We have this way to think is a general way to think. Just I am applying this concept to this particular family of algebra, but if you check all the idempotent ideals associated to these vertices inside the relation, all these idempotent ideals are non-homological. Just I need to draw what is the relation, and the idempotent ideals associated to each vertex are non-homological, and this guy outside the relation are always homological. And the question that we answer using Brauer configuration algebras is how many of these guys are in this family of algebras. So we found an unexpected relation between the world of combinatoric stuff in representation theory of algebra and Brauer configuration algebra, which are a new tool in representation theory of associative algebra. Here we have some lemmas which describe something that I said before. I mean, every idempotent ideals inside the relation is a non-homological ideal. Also, we have a dual result when you have commutative relation, not just a linear relation. And here we have all the possible combinatorial cases. So I mean the combination of these idempotent ideals are described in all these lemmas here. And just to end, I would like to mention that if you compose idempotent ideal which is associated with a vertex inside of the relation with one guy outside the relation, this new idempotent ideal is again a non-homological ideal. So we have an interesting way to count these ideals, just drawing a quiver and put all my attention in the relation. But also we can describe this number of non-homological ideals by using the word induced by the Brauer configuration algebra in my example. So the combinatorial information inside the Brauer configuration algebra give me information in another topic, which is the homological ideals. In the same way, we have here the number of homological ideals because are dual. This concept is dual. And we also have the chance to introduce some arrays like Ringel arrays, which satisfy some very nice properties. We can also describe all the elements inside this triangle in a recursive way. And this guy here gives me information about the Nakayama algebra and its corresponding homological or non-homological ideals. Here is the formula to describe all the guys inside the triangle, and this triangle is related with this Zumkehl triangle, which is really important in the context of Dedekind numbers and many things in combinatorics. And just to end, this is the homological triangle. This heat triangle encodes all the possible, all the numbers of homological ideals inside this algebra. And I would like to say that this triangle allow me gives or a new partition formula as in the same way of Ringel and Farr. Here we have our formula, but instead of use this D, which were introduced by Ringel and Farr, we can use this formula here, which are close related with the number of homological ideals. Here we have the new version of Ringel and Farr theorems, and here's some reference of our work. Thank you very much for your attention. Sorry?
In the definition of Nakayama Alpebras, it mentioned admissible ideal.
Yeah, we fix this ideal. You can fix any ideal on this linear-oriented algebra. Like this. This is the ideal that you fix. And also you can fix here, in this case, that is the so-called type 2 of Nakayama algebras. But we can, in this talk, study these algebras, like here. No, you can delete a path inside this arrow. So, for instance, you have here a relation between, or ideal, it means the path between I and I plus k here. So you delete a path of length k on this quiver. This is the admissible idea.